welcome everybody to the first Philadelphia Future City Engineering Fair webinar. Our speaker today is Dr. Bruce Betts, who is the Chief Scientist and Light Sail Program Manager for the Planetary Society. He has a bachelor's degree in physics and math and a MS in applied physics from Stanford. He also has a PhD in planetary science with a minor in geology from Caltech. Bruce studied planetary surfaces, including Mars, the moon, and Jupiter's moons using infrared and other data, and has published a number of scientific papers on these subjects. Dr. Betts also spent 3 years at NASA headquarters, managing planetary instrument development and programs to design spacecraft science instruments. At the Planetary Society, he's managed a number of flight instruments, both science and public outreach projects, including silica glass DVDs on the Mars exploration rovers and Phoenix lander, carrying millions of names and Mars literature. The life biology experiment that flew on the Russian Phobos sample return mission, a NASA grant studying microrovers to assisting human exploration. He is very notably the program manager for the Planetary Society's light sail and solar sail missions. He is also the author of several books for kids science, including his most recent that I believe just came out last month, Space Exploration for Kids, a junior scientist's guide to astronauts, rockets, and life in zero gravity. So I think I will just at this point hand it over to Dr. Betts, and he will tell us, give us an introduction to the moon and the lunar surface. Bruce, it's all yours.
Great, thank you, and thanks and hello to everyone. It's great talking to you today. I'll be giving you that introduction to the moon and all sorts of aspects of it, and also focus on the lunar surface. And then my impression is in later talks from others experts, you'll hear more about details of certain aspects of it. So let me see if I can share my screen here. Ken, can you see it?
I can see it.
All right, good. So this is an actual picture of the lunar surface from Apollo 17, the last of the human missions to the moon. And I'll get that little pointer out of the way. We've already had my introduction. I'm from the Planetary Society, which is the world's largest space interest group, a nonprofit with members, adults, and kids from all over the world, supporting and interested in space exploration. So let's start with the all-important first thing, which is, what is a cow's favorite place in the solar system? The moon. Don't worry, that'll be the last pun that we'll have. Well, I don't make any promises. So let's talk about the moon more seriously. There's a picture that I took of the moon with some clouds and foliage. And you can think about just what you can tell from just looking at it with your eyes, which is probably a little bit worse than this, but you can see there are bright areas and there are dark areas. The bright areas we've learned are highlands. They tend to be higher locations and they have one composition of rock, and they're left over from the original formation of the moon. And then the dark areas are kind of like basalts that are volcanic rocks, volcanoes that flooded the that flooded the impact craters. We'll talk more about all of this, but just to give you a start, you can see stuff with your eyes. All right, so a little random space fact for you. The moon is much smaller than Earth. So if the moon were the size of a tennis ball, the Earth would be roughly the size of a basketball, which we can see in this image. So the moon is significantly smaller than the Earth. And also you notice just from looking at the moon versus the Earth, some things are really different. You don't see oceans, you don't see water, you don't see clouds. That's because they're not there. There's no surface liquid water. There's no clouds. And in fact, as we'll talk about more, there's no atmosphere. There's no air on the surface of the moon, or essentially none, which makes for some different things. But notice here, the moon is right next to the Earth, so obviously it's not to scale. Let's look at what it looks like to scale. So that's the Earth and the moon, if you can see it on the screen, are to scale here. It's 400,000 kilometers, about 250,000 miles in between the Earth and the moon. And so it's far away. About 30 Earths would fit in between the Earth and the moon if you put them next to each other. So to give you an idea, one of your first challenges in thinking about doing things on the moon is just getting to the moon. If we go back to this, the International Space Station, which orbits the Earth about 400 kilometers up. So on this scale, it would be about 1 pixel right next to the Earth. So we think of that as space, but it's another 1,000 times farther to get to the moon. All right, let's take a closer look, telescopic, or actually in this case, spacecraft look at the near side of the moon. As you've probably noticed and probably learned, we always have one side of the moon facing the Earth at all times. This is called tidally locked, or in synchronous locked rotation. And so as the moon orbits, it's always pointing the same side at Earth. And that's something that evolves naturally from tides, basically different parts of the Earth pulling on different parts of the moon. You advance time over millions and billions of years, the Earth's gravity tends to grab a hold of the moon in such a way that you end up with one face pointing towards it. That's true of other moons on other planets in the solar system if they're close enough to their parent body. What else do you notice? Do you notice, oh, by the way, I'll take all the questions at the end. You can put them in sooner, but we'll have you type in questions into the chat, and then I'll take as many as I have time for at the end. So you notice, again, dark areas, bright areas. Bright areas, highlands, dark areas, what are called mare, and are volcanic flood basalt, basically, whereas the highlands formed from essentially freezing out of the initial moon. And we'll talk about moon formation in a little bit. You also notice these, what we know now are craters. And we'll talk a lot more about that, but it's when asteroids slam in, or comets slam into the moon, they throw material out and they create a circular hole with material that's sprayed around the moon. And in fact, notice that the mare, some of them are circular. They're from gigantic impacts that are hundreds of miles across. Later, basalt lava flowed into those areas. People used to think the dark areas on the moon were seas, that they were water. They are actually dark rocks, like from some volcanoes. Let me know if I just got a message. My internet is flaky, but let me know if you have any issues seeing what I'm showing or hear me. All right.
Your sound got a little fuzzy for about 5 seconds. It's okay.
Okay, but we're okay now. Thank you. Let me know if there's a problem. So this is the far side of the moon, which we never saw or could see until spacecraft. So spacecraft got to the other side of the moon, showed us this. It surprised scientists because what do you notice is missing? All those large mare. And you do have some small ones, but indeed as part of the tidal process of grabbing hold of the moon and eventually getting one face facing the Earth, it relies on the mass distribution of the moon, and the mass distribution of like how heavy one side is compared to the other ties to these mare and the impact craters. And so that's why you end up with this feature. So realize that if you have anything on the other side of the moon, the far side, which we're looking at now, There's no way to directly communicate with Earth. You have to communicate with relay spacecraft, which is why most all of the landers on the moon have landed on the near side so they could communicate directly with Earth. There's now a Chinese lander and rover on the far side of the moon that uses a relay satellite. Now we're looking at the north pole of the moon. So we're only looking at a portion, not a whole hemisphere. And again, notice craters, lots and lots of these impact craters that have happened over time. And here we have the south pole of the moon. Now what's interesting, and we've learned over recent years, decades, is that some of these, let me see if my little pointer works, some of these craters near the pole are deep enough that, and the orientation of the moon is such that they are permanently shadowed. They never see sunlight. And so they get extremely cold. So even though there's no atmosphere and you'd think, and water is very unstable elsewhere on the moon, we've discovered there's water ice in some of these permanently shadowed craters. And there are also tops of peaks that are permanently in sun. All right, let me show you something spiffy. This is a video, a combination of pictures taken from the Discover spacecraft, which is between the Earth and the sun. And so it actually, as the moon passes by in front of the Earth, it's actually seeing the far side of the moon, the opposite side that we see from Earth, because it's farther away from Earth than the moon. And that's North America, by the way, that's just above the moon as it goes by there. We also see phases of the moon. This, if hopefully you can see it not under pictures, is a one phase of the moon. There's also a little dot on the left side. This is another picture that I took just with a camera, and that's Jupiter, which looks like a bright star. Here, a crescent phase of the moon with, in this case, the planets Venus, the bright one, and Mars, the little tiny dot. So you've probably learned this probably over and over, but let me go over it again, which is phases of the moon. And this is more significant looking from Earth, but it also will lead to understanding what's going on with the moon more. So this is from actually one of my books, a diagram they did from Astronomy for Kids. On this inner circle here is the orientation of the moon relative to the Earth, not to scale, because it would be much farther away, with the sun's over coming from the right side. So sunlight's coming from the right, and then this shows what you would see from the Earth. So let's start with full moon. The sun is illuminating the near side of the moon completely, so we see it fully lit. But when you're over here, at let's say at first quarter moon, when you look up in the sky, you're seeing half daytime and half nighttime. And just like over here, you're seeing the opposite of half daytime, half nighttime. So the sun's always coming from the same direction. There are people refer to, and there's the dark side of the moon, which is a misnomer. There is a dark side of the moon, but it keeps changing. So it's not one side of the moon. Just like the Earth, half the Earth is dark at any given time. It's nighttime there, it's daytime on the rest of the Earth. But it changes. Well, it changes on the moon, but the moon, instead of having a day that's 24 hours long, has a day that's 29 and a half Earth days long. That means you have 14 and a half, roughly 14 days of Earth days of daytime in sunlight if you're on the surface of the moon. But then you have over 14 days, Earth days, of nighttime. And so if you're designing a city on the moon, this is going to be one of your huge challenges, is that you have sunlight for a couple weeks, but then you have darkness for a couple weeks. And so it wreaks havoc with power, wreaks havoc with temperatures. So the moon, because it has no atmosphere, it heats, and also the surface is very fluffy. There's a lot of dust. It heats and cools very, very quickly and in extreme ways. So for most of the moon, during the daytime, it's hundreds of degrees. Pick your system, Fahrenheit or Celsius, it's hundreds of degrees. At nighttime, it's minus hundreds of degrees. It swings something like 500 degrees Fahrenheit, 300-ish Celsius from daytime to nighttime, and that's an issue. The only place that you don't have this is permanently lit places, which are always hot, and permanently shadowed, which are always cold, but they only occur in small regions near the poles of the moon. All right, how did the moon form? Well, this is kind of a weird surprise. This was only determined with the return of rocks from the moon in the 1970s that helped tell the tale. The most likely, by far the most likely theory for how the moon formed was that the Earth formed about 4.5 billion years ago. And then sometime within a couple, 2, 3, 400 million years after that, a huge body like the size of Mars, so a planet-sized body, slammed into the Earth. And when it slammed into the Earth, it threw a bunch of material out. And a lot of that fell back on the Earth. But some of that went into orbit around the Earth and formed into the moon, and that's where the moon came from. It's part of what explains why the moon is much less dense than the Earth. On the Earth, when it formed, it was hot, molten. The heavy stuff like iron mostly went to the core, whereas the moon was formed from the stripped off rocks, the silicate rocks in the upper part of the Earth. So so the moon also very, very old. Now what's interesting, different, I should say, what's really different about the moon, there are a lot of things, but because it has no atmosphere, and it has no liquid water, you don't have the amount of erosion. You don't have any water erosion like you do on Earth. You don't have any plate tectonics like you do on Earth. And so the surface is not resurfaced or eroded or subducted in plate tectonics. The surface just sits there and it gets affected, but it gets affected by sunlight and particle radiation and by impacts of asteroids of stuff hitting the surface at very high speeds is one of the primary, it's the primary geologic mechanism on the surface of the moon. On Earth, we've been hit just as much, but most of the stuff hit early in the solar system in the first billion years of 4.5 billion years. And on Earth, between plate tectonics, water erosion, chemical erosion, weathering, all of this, most of this has been erased. So there are only a couple hundred impact craters that are visible on Earth today, but there are literally billions on the moon. So it actually gives us, the moon is like a time capsule for our part of the solar system, telling us the impact history of the solar system, and particularly our part of the solar system and how much impact was significant. You can see this is one of those highland bright regions are older because the lavas in the dark regions came in and flooded and formed younger surfaces, still mostly like 3.5 billion years ago. But the highlands are even older. And this is a picture from the highlands where you can see there's so many craters that when later craters came in, they just erased other ones. There were as many craters as you can fit on here. And that in partly is that's how we date things in the solar system when we can't bring back rocks. We use the moon and what we've learned from bringing back rocks and dating them to learn things about dating other places. And when you see a lot of craters on a planetary surface, you know it's very old. It hasn't been heavily eroded. Speaking of old rocks, now this is going to be a technical experiment. I'm hoping this works. If not, it's just a 1.5-minute video, but it's from a Planetary Society series of internet videos called Random Space Facts, and you'll probably recognize not just me, but someone else in the video. So let's give it a try. If it doesn't work, be patient. I'll be back in a 1.5 minutes anyway.
Hey, Bruce, there's no volume coming through.
All right.
No audio on that.
Grandpa's Space Pants. All right, so you're hearing my audio?
Hearing you.
All right. That's my boss at the Planetary Society, Bill Nye. All right. Well, I don't think I can fix it quickly. It's very funny if you hear the audio, just trust me. Now, you can actually find all those at planetary.org/RSF if you're interested.
Okay.
And
I'll add a link to it when we post this video
okay,
of this.
I can give you links to the specific videos. I have one more later in the presentation, otherwise not. So the whole point of the video was that most Earth rocks are older than most moon rocks are older than most Earth rocks, because the surface is older and the Earth has been resurfaced. All right, so here's some other characteristics of the moon, some of which I've mentioned, some of which I haven't. It is the 5th largest moon in the solar system. It's by far the largest compared to its parent planet. And as we mentioned, it's about tennis ball versus basketball size with the Earth. Has essentially no atmosphere, length of day 29.5 Earth days. What I haven't mentioned is it has about 1/6 of the Earth's gravity. And so that actually could be a benefit in city planning, but it all means that moving things around, physics work is going to be different, because something that weighs 100 pounds on Earth is going to weigh about 16 pounds on the moon. If you watch astronauts moving on the moon, they tend to hop and jump a little bit. And it's just a different situation. All right, we're going to look at more lunar surface, and not surprisingly, we see more craters, lots and lots of impact craters. Now, this is actually a picture from the mare. So you can see now in those dark volcanic rock-filled areas of the moon, you don't see as many craters. There's still plenty, indicating it's an old surface, but they're not nearly as many as we see in the highlands, indicating it's a younger surface. You can also see some interesting things, like probably what's the rim of an older crater that's been then filled in by lava. You can see, if you look at this crater, you can see the material, which is called ejecta, which has been thrown out from there. And to throw in a couple other words, one of which I know you're getting a whole talk about later in this series, the upper surface of a planet that's been beat up by impacts is called the regolith. Regolith. And so that's what you're dealing with on the moon. It's an impact generated dirt, soil. It's not technically a soil, but it's the equivalent of soil on Earth, but it's all generated by impacts, slamming in, breaking up rocks, forming dust, forms the regolith. And then a really fun word, I just enjoy saying it, is the upper kilometers of the surface gets fractured, and that's called the megaregolith. There you go, megaregolith. It's fun to say. Try it sometime. Okay. Here we've got a picture from a spacecraft, obviously in orbit, around looking towards the edge of the moon. Notice we see black sky. We don't see atmosphere. And we'll notice on the surface of the moon, even in daylight, the sky is black because there's no atmosphere to scatter the light like there is on Earth, making for a blue sky. These are impacts upon impacts. Oh, let me show you one other thing here. So these are called wrinkle ridges along here, and that's because the lava filled in, and then as it cooled, it's kind of like brownies or cakes. Sometimes as they cool, they contract, and so you end up getting different cracks and overlying smooshies. It's a technical term. It's not really. All right, here's a very large crater, hundreds of miles across, seen from a spacecraft in orbit around the moon. Notice large craters end up with mountains in the middle. And that's kind of like if you drop a rock into water, it'll rebound in the middle and it'll splash upwards. But because it's water, it just flows back out. If you hit a bunch of rock and you make molten rock and it comes back up in the middle, it forms into mountains. In fact, I think the next picture we have, this is the central peaks inside a large crater on the moon. taken, again, a high resolution image, in this case from an orbiter that's still in orbit, doing great work, making amazing pictures of the moon, called Lunar Reconnaissance Orbiter, or LRO, NASA mission. Interestingly, on the moon, you get impacts all the way from hundreds of miles across to tiny, smaller than you can see with your eye. This is a scanning electron microscope picture of a little ball of melt glass that is smaller. You could probably see it, but it's tiny, 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 kind of width of a human hair size. And on that piece of glass is an impact crater. That's because there's no atmosphere. If a piece of dust or a piece of sand-sized particle hits the Earth's atmosphere, which it does all the time, 300 tons of this material hits the Earth every day, it burns up because it's going really, really fast, and the friction causes it to burn up long before it reaches the surface. That's what a meteor is the streak of light caused by that. But on the moon, you have what are called micrometeoroid impacts all the time. And one this tiny probably isn't of concern, but the larger impacts that are from small stuff, which hits more than big stuff, is something you have to deal with when you're on the moon. And if you're on the surface of the moon, things need to be sturdy enough and protected enough, including astronauts in their suits, to survive the impact of small objects traveling at an incredibly high speed. This is just one other geologic feature. Apollo 15 landed near this. It's called Hadley Rill. And what it is where lava flowed in a channel. So it looks kind of like a river channel. Well, it's kind of like that, but instead of water causing it, lava caused it. And we see this type of thing on Earth as well. So the moon is the most explored place in the solar system besides Earth, not surprisingly, because it's by far the closest. I said how far away it is. It's much closer than any of the other planets or asteroids, at least usually. Almost 100 missions have been flown or attempted to the moon. A lot of them failed, particularly early on, but those included, almost all of those were robotic. They had ones that just flew by the moon early on, orbiters that go around the moon we're still exploring that way, landers. There's active Chinese lander on the surface of the moon right now. There have been many American and Soviet landers. But the other significant thing about the moon is it's the only other place humans have walked on besides the Earth. 12 astronauts walked on the moon between 1969 and 1972. And there may be more in this decade. Certainly there are attempts to do so. So this is from Apollo 11, the first humans on the moon. This is Buzz Aldrin, the second person walking down the ladder as Neil Armstrong took a picture of him, who was already on the surface. Notice daytime, black sky. Black sky because there's no atmosphere to scatter light. Bye-bye. Here's Apollo 12. Notice that the surface is covered, it's probably hard to tell, but it's covered in a fine dust. There's some rocks, but where they landed was mostly flat, which is pretty good if you want to build something. And by Apollo 15, and then now this is 16, they had a lunar rover. So basically a car to drive on the surface of the moon so they could go farther. Again, you see some hills, fairly flat. You see footprints in the surface, which by the way, are still there and will be for millions of years, because the only thing really affecting them is meteorite impact, and that's infrequent. But look at this, same Apollo 16 nearby. They've driven to this area. There's an impact crater. And so you've got, and you can see all the small craters on top of the big crater, which for the moon isn't even that big a crater. So you've got a very rough surface to think about and deal with in your planning. This is Apollo 17. You can see the big rocks that have probably formed, and then they're thrown out by impact craters, and that's where they get distributed on the surface. There are hills off in the distance. You've got a human for scale and a lunar rover for scale. Got another video. rather than trying to solve the audio problem, I'll just tell you what's going on. It's basically Apollo 17, they broke a fender on the lunar rover. And so they actually pulled out maps and duct tape. And using maps and duct tape, they fixed the lunar rover. And here in the shtick, I'm building a fender replacement in the background. This is actual footage from Apollo 17, and there they are fixing things. So this is the kind of stuff you do if you are on the moon and don't have much in the way of supplies. They formed that, and this is what I formed. Oops. And there's Bill again, Bill Nye. He's letting me know that there's a meeting that I'm supposed to be at. He finds it a compelling pedagogical moment. Meeting in 5 minutes. I'm good. And off to the meeting. All right, we move on. This is interesting. With Lunar Reconnaissance Orbiter, basically has a camera big enough, it's got a telescope essentially on the spacecraft. It's very, very much like a spy satellite on Earth. And so it's actually able to see what's left on the moon. In this case, from Apollo 17, they leave the bottom part of the lunar module on the moon when they blast it off with the top part. But notice you can also see footprints still on the surface. This was taken just in the last few years. So footprints from 40 years ago, and you can see tracks from the lunar rover that are still there. And of course, little impact craters all over the place. All right, I've tried to summarize, in addition to what we've talked about and also repeating some of it, some of the challenges in city construction that you would have, because no one's ever done such a thing on the moon, although there's been a lot of discussion, but it would be really, really hard. And so first, you got your challenge of just getting there from Earth. So getting people and supplies there. We haven't flown humans there since 1972 because it is very, very challenging. We've sent a lot of robotic spacecraft, but they're smaller, lighter, and you don't have to keep them alive. So you got a challenge of getting there and resupplying. There's no atmosphere, so there's no air to breathe. You have to bring it or make it. There are 29 Earth days and 1 moon day, which means you have to deal with these periods of darkness of 14 days of darkness, unless somehow you set up in the permanently lit locations at the poles, but those are few and not very large, and also harder to get to in an orbital sense. If you're on the far side, as I mentioned, you need communication relays. There are huge temperature extremes of the surface, hundreds of degrees, and so that's going to affect anything you put on the surface. Has to be able to deal with the thermal changes, expansion, contraction, the heat and cooling of the being in the really, really hot and the really, really cold. And there's one other thing you have to deal with. This is Harrison Schmitt, astronaut on Apollo 17. And if you look at his spacesuit, it's covered in dust. There's all sorts of dust. And this dust is fine silicate particles. They can be sharp and jagged, and they kind of they stick to everything. They also cause the astronauts some issues with lungs and nose not being happy when they're back inside the spacecraft. So you got a lot of dust to deal with, something to think about. You also have radiation. So on Earth, our magnetic field and our atmosphere protect us from a lot of the radiation, harmful radiation. That includes light radiation, things like gamma rays and X-rays, and most ultraviolet. When they hit the top of the Earth's atmosphere, they get absorbed and they never make it to the surface and do damage. That doesn't happen on the moon. You also have particle radiation, protons, and the like being sent out in the solar wind from the sun. These things are not healthy for people, so you have to figure out a way to shield from the radiation when you're on the surface of the moon. There's rough terrain, we've seen that, although you can choose your location to help a lot with that. 1/6 Earth gravity, not necessarily bad, but you have to keep it in mind. there's a lack of resources. There's plenty of rock and things you can mine out of the rock, but there's frozen water, but only in the poles. And so there's just a general lack of resources, although if you're clever, you can come up with ways to use what you've got, but you're still going to have to bring supplies in from Earth. And then this micrometeorite impact issue that you're getting, things are going to get hit by uh, bits of sand or dust, which don't seem that dangerous until you realize they're going several miles per second, tens of thousands of miles per hour. So they have a lot of energy nonetheless. All right, now at the end, before I take questions, I just want to mention something else I'm kind of passionate about, which is, hey, go out and look up at the night sky. And there's really cool stuff to see in the night sky right now that's easy to see. And that includes the moon. So in the evening, in the east and the south, you're going to see super bright red Mars. Now Mars changes distance from the Earth because of the way the orbits the interplay between the orbits. So we're actually at a point where it's going to be closest to Earth for the next several years, certainly for the next 2.5 years till it comes back around on October 6th. So just a few days. So right now, Mars is about as bright as Jupiter, which is quite rare. And it looks orangish, reddish, very easy to spot. If you go out in the evening, look in the east or the south, there's going to be a really bright orange looking thing. That's Mars. Tomorrow night, October 2nd, go out and look at Mars looking super bright right next to an almost full moon. And that'll be cool. In the evening west, you can also see very bright Jupiter looking as bright as Mars, but looking white. And then yellowish Saturn is to the left of Jupiter. So if you see a bright star-like object, it's Jupiter, and the other much less bright, but still bright star-looking thing is Saturn. And then if you're up in the pre-dawn, look in the east, and you'll see super bright Venus, which is brighter than all these things. And those things change over time as we go through our orbits. So particularly Mars now is an excellent time to see Mars. Mention the books I've written, here they are. There's the new one, Space Exploration for Kids. Astronomy for Kids gives you easy things to look for with just your eyes, binoculars, telescope. Super cool Space Facts is kind of what it sounds like, little descriptions of everything. You guys are probably all ways past my first book of planets. VR Space Explorers is a fictional story, and Space Exploration for Kids is a focus on human exploration. So here are all sorts of things. You can find me on social media. You can go to the Planetary Society, listen to planetary radio that includes interviews with scientists and engineers. You can look through for other sources of information on the Planetary Society website, planetary.org, find random space fact videos. I also have an asteroid defense class that's free to take about an hour. And for those up for more stuff, there's a whole introduction to planetary science and astronomy class. So it's kind of intro college level, but it's mostly a pretty picture show with information about the planets. And that's also at planetary.org/Betts class. All right, let us move to questions if you've got them. And I will stop sharing and check the chat. Okay, that's all. From Beer. Why isn't the moon pulled towards the Earth if it's within Earth's gravitational field? Good question. Because it is in orbit. So it's kind of like if you put a tennis ball on the end of a string and you spin the string around, that, or if you think about carnival rides, that ball's going to want to be pulled outwards, and that balances the gravitational force pulling it inwards. So it's the fact that it's the same reason we don't get pulled into the sun. It's the movement. It's moving very, very fast in its orbit around the Earth. And in fact, it is actually getting farther from the Earth over time, but that's a more complicated thing. That's due to tides and actually losing energy over time in the system. So a little tiny bit about it actually, here's another random space fact for you. It gets farther from the Earth at about the same speed that your fingernails grow. So centimeter, part of an inch each year. All right, what else we got? I'm getting behind. Good questions. I'll answer faster. If the moon gets hit by a very large asteroid, what will the effects be to Earth? It depends on how big. For most impacts, it would have no effect whatsoever. Although we have seen, if you're looking through a telescope at just the right time and the impact's big enough, you might see a flash. But all the material is going to fall back to the moon. If it were hit by a huge asteroid, it could actually throw material out, which would then, some of it would hit Earth. Most of it would burn up in the atmosphere. But the good news is there aren't many of those large things flying around the solar system anymore. Does the far side have less meteor impacts because of the less black spots? It actually has more impacts because the brighter areas, the highlands, tend to be older. It's kind of saying, so it's an answer. Is there regolith underground, and is it made of similar materials? Yeah, the upper few meters, the upper few yards of the surface are all considered regolith, and it's this broken up, impact broken up materials that are all similar. If you go farther down, then it's more fractured and untouched. If you go miles underneath, then it's not, depending on where you are, not as affected by impact, and is going to be either the original solidification of the rocks from the original formation or lava that's solidified. Is there a certain material that astronauts use to stay warm or cool depending on the temperature? They basically insulate their spacesuits very well. So the spacesuits are actually made of lots of different layers, and that helps protect them from heat or cold, and then also the protects them from micrometeorite impact. Their biggest concern, usually because they haven't had astronauts in 14 days of night, is the heat, and that's why astronaut uniforms are white, because that reflects the light and causes less absorption of heat. Why does the far side have less meteorites? Well, as I mentioned, it actually has more. I guess what I'm missing here, part of, if you look at the giant asteroid impacts, there are fewer that have been filled in by mare. And we think that's basically just statistical, that you happen to get more impacts on the one side of a large size. But also, it's more complicated because the side with more mare has had is less thick in terms of the solid stuff on the outside of the moon, and so more lava was able to come up, so it actually makes it look like there are even more large impacts, whereas you can find them on the other side of the moon and even the polar regions, but they've been covered up so much by other impacts that they're not as obvious. Sorry, working on it. And how would increasing gravity on the moon affect Earth? Well, one, it's a theoretical question because you wouldn't be able to increase gravity on the moon without adding a lot more mass and a lot more mass. And if you did have that effect, then you would necessarily change the orbit. It would temporarily pull the moon closer, presumably. Again, this is all hypothetical, but then it would stabilize with a higher speed balancing, or you'd be closer in, but then you'd reach a balancing point of the speed and the gravity. But we don't have to worry about that. Is there any magma or iron core at the center of the moon? There's definitely some iron core, and there's actually still trying to figure out whether any of it's molten. So the Earth has part of its core is molten, it's liquid. And that's part of why we have an active magnetic field, is that conductive material moving inside the center of the Earth. On the moon, we think it's probably solid, because basically if you've got a smaller object, it's able to cool faster over the history of the solar system. It releases heat that's deep down, releases it out to space. The Earth is big enough and hasn't things going on that hasn't been true. It also has radioactive materials, so does the moon, but again, having the smaller surface area compared to volume, you end up keeping stuff molten on Earth, whereas with the moon, may or may not be molten. But if it is, it's a very small part that's molten, liquid. Is there magma? Same answer. There certainly was a lot early in the solar system, but after billions of years, you had cooling that occurred. Could the magma or iron core at the center ever be used as a heat source, or is it completely cool now? No, there's still heat, and in fact, some of the measurements the astronauts did was pounding temperature probes into the upper couple meters of the surface, up 6-8 feet, and measure the temperature change between down low and up high. And there is a temperature gradient. There is a change, and so you do have warmth down low, but it's unlikely. It's so little. It's not a very plausible heat source for anything practical. It's still warmer inside, in part because there's still things like uranium and thorium that are decaying and warming things, keep things warm deep down. Is there any residual thermal energy that's trapped in between the layers of the moon? Yes. There's residual even left over from formation, but it's not that much by now. A lot of the heat inside the moon is coming from radioactive decay that happens. All right, I'm going to review, but I think I caught up. Oh, no, there are questions higher up. A lot of schools.
Bruce, there was one right near the beginning. I think this was when you were showing a picture of the far side of the moon. Why are there little glinting spots on the moon?
Thank you. That was what I was looking for. Are those clusters of the salts? No, they're just why, since now I'm not looking at the picture, I'm not sure the exact answer, but there aren't clusters of salts, or at least not much on the moon, but it's interesting, and you probably, from just the fact that you asked that question, may be aware that there are on the largest asteroid, also smallest dwarf planet, Ceres, which has some very bright spots, which are thought to be from liquid water that's come out and put salts on the surface. But on the moon, we don't have evidence like that of the salts. So probably just a brighter area, brighter rocks. Most of the moon is quite dark, but there are brighter rocks, particularly in the highlands. All right, did I miss anything else? I don't think so. Any last questions? Last chance.
I think there was a last question here. How would radiation affect the surface of the moon?
Got it. Thank you. That's a good question. It actually darkens the surface of the moon. So if you look at more recent impact craters, and you can see them on the near side, even with your eyes, but certainly with binoculars, there are some impact craters that have bright rays, basically lines of bright material coming out. It's because when you sit on the moon, and again, this is over long periods of time, the radiation has an effect that it darkens the rocks over millions of years, billions of years. And so when you get an impact and it digs into the lower surface, it throws brighter material, and then it starts to darken, but over very long periods. So you can actually distinguish some of the, especially in the Mare type terrains, you can distinguish the younger impact craters by the bright rays that come out of them. They don't have a lot of other significant effect, although there is some implantation of material in the upper surface of hydrogen and the like that get implanted. Let's see, we got more questions. If we were to hypothetically cause carbon dioxide pollution on the moon, would it be contained or would it float through space? It would probably temporarily be contained, but then it would float through space. Some of it would actually probably collect as carbon dioxide frost, dry ice, just like the water has migrated to the polar regions in this. But water, turns out, water ice at really cold temperatures is even more stable than carbon dioxide ice. But there's just not enough gravity on the moon to retain an atmosphere for very long. So would that darker material be able to absorb sunlight and heat over time? Yeah, so I mean, not so much over time, but on a daily lunar day basis, dark materials, just like on Earth, asphalt versus concrete, they're going to heat up more. But they're also going to cool off extremely at night. But yeah, the dark materials are going to absorb more of the solar radiation, solar light. All right. Oh, then could we use that as a potential way to contain energy? Only temporarily if you could find out some way to use it, because it's going to cool off at night as well. But you do have very hot rocks on the surface. So if you could figure out some way to convert that, not being an expert in such fields, I don't know if that's plausible. I'm not aware of any way to do that. All right, we're about out of time, and I think we're out of questions. So thank you all. I appreciate your taking the time. I hope this was interesting. And thank you to Ken and Karen and everyone involved in putting this together.
And thank you, Bruce. We greatly appreciate you giving us your time for this. I'm sure the kids learned a lot today, and I'm looking forward to seeing their cities in January when we have the competition. I'm
Yeah,
sure
good luck,
they will
everyone.
think up some great stuff.
Good
And we'll
luck and
try to
enjoy.
get you a Future City t-shirt.
Okay, good.
You'll
Thank
probably
you.
have a picture of the moon on it this year.
That would be ideal.
Okay.
All right, thank you.
All right. Well, thank you, everyone. We're going to sign off now.
Thank you, Dr. Betts.
You're welcome.
Thank you.